Yeah, it's a pleasure to be here at this great campus and institute. First time here at BIMSA, so it's my real pleasure. The talk will be about positive geometry in particle physics and cosmology. In short, positive geometry is a new emergent field of mathematics that's related to and inspired by physics. So the point of my talk today is to give you some overview of where that comes from, what is this about. It's also related to, you see a symbol up here. It's also related to some funding. It's also related to some research projects. So I'm going to also tell you about that context, which I hope may also be interesting for you in terms of activities that we organize. So this is the outline of the talk. I'll begin by saying a few words about this project. It's called Universe Plus. And then I'm going to describe you the cast of characters. I'll introduce the main players, scattering amplitudes, what is the main idea behind this positive geometry concept, and also explain how it's related to certain topics in theoretical cosmology, or cosmological correlators. And then finally, I'll give you like some appetizers of current research so that you get some flavors of what this positive geometry could stand for. So to begin with, as I said, this is a project funded by the ESC. It's a synergy grant. That means there are several PIs. Actually, we are a team of 4 PIs. And so it unites people from these different areas. So we have particle physics represented by myself and by Nima Akani-Hamed. We have cosmology, theoretical cosmology, there's Daniel Baumann, and mathematics, the PI collaborator Bernd Sturmfels from Max Planck Institute for Mathematics and the Sciences. And in a nutshell, what is this positive geometry? So it turns out that in certain problems in particle scattering and also in early universe cosmology, certain geometric structures have appeared that share common features. And this inspires us to develop this subject more systematically, and we call it positive geometry. And we believe that to really do that properly, to find the positive geometries that describe our universe, to go beyond certain toy models where we see these first hints, we really need also help from serious mathematicians. So that's why it's this combination, collaboration between physicists and mathematicians. And I think here at this institute, it's probably exactly the right place to talk about such cooperations. We started, I'll say more bit about the timeline. We started last summer, July 2024. It's a 6-year project, so we're just really beginning and starting out. So these I just mentioned in passing, these are the institutions. So we have 2 institutions from Max Planck in Germany. I'm based in Munich. Here you see a picture of our new building. Maybe not quite as nice, but also nice. Not quite as nice as this campus, but also quite nice. Max Planck Institute for Mathematics and the Sciences, just a short train ride away in Leipzig. Daniel Baumann is at the University of Amsterdam. And finally, there's the Institute for Advanced Study in Princeton. All right. So these are the partners. So let me, as I said, let me begin by giving you some flavors of these different themes. So the first is scattering amplitudes. That's my core area of study. So what are those scattering amplitudes and where do they come up? So they're really a crucial ingredient when you want to compare outcomes of collider experiments with theoretical predictions. So here on the left-hand side, I've taken a slide from a phenomenology colleague, Fabrizio Caola, where on the very left you see what happens at CERN, at the LHC experiment, and then here in the middle you see a theorist's cartoon of such a proton-proton collision. And the details are not so important for this talk, but you can see that there's many layers. So it's a complicated process actually of conceptualizing, starting from fundamental QFT, conceptualizing these different layers in this process to connect to what actually appears in the detector. So for the purpose of my talk and our research, we're really focusing on these innermost layers where at high energies, we can take the QCD Lagrangian and really describe the high energy processes in terms of that Lagrangian, in terms of in the regime where it applies, also in terms of perturbative Feynman diagrams. Now, of course, as I mentioned, there's a lot of other relevant non-perturbative physics, but that is another story. So that's kind of the experimental and pheno side of scattering amplitudes. Now, here on the right-hand side, you see the three of the protagonists, really in some sense the founders of a modern amplitudes field. And I'd like to quote Lance Dixon, who said, to him, scattering amplitudes are the most perfect microscopic structures in the universe. So what does he mean by that? Well, to me, that signifies, that kind of expresses the idea that scattering amplitudes are not only useful to describe experiments, but they're also beautiful from a conceptual and mathematical viewpoint. And so in the amplitudes community, therefore, actually, it's very important also to look at this structure in terms of analytic data for amplitudes, for formulas, algorithms, concepts, and somehow not just the also very important numbers and plots that we have to compare with the experiments. So I'd just like to underline this viewpoint, because from an experimental viewpoint, perhaps one could say these formulas, they're just some intermediate expressions. Maybe we don't even need them. Is it worthwhile writing them down and putting them in some files? For us, they're very crucial, because they hold a lot of information about the structure. And it's precisely those structures that gave us hints for these new mathematical objects that I'm going to describe. So just to say a few words about the experimental context. So we at the LHC, we can look forward to many years of more data taking. So I think it's also a good time to develop further our amplitudes methods to really help reach the theoretical precision that's needed to match the expected experimental precision. But for me, and from the point of view of this talk, it's just some context. So today I will focus more on the beautiful mathematical structures. But of course, it's good to have this motivation also in the back of one's mind. Now, just a few words for those who are not working with amplitudes. What are they? How do we think about them in perturbation theory? So here's just some sample process in QED. So in principle, we could go back and use Feynman's method. We could go to open a textbook if you want to describe such a process in perturbation theory. All we have to do in principle is to write down the Feynman diagrams and translate them according to the rules into some algebraic expressions. So for example, here at the lowest order, there's no interaction, nothing happens. The first connected diagram is what we call tree level. That's leading order then in the terminology. And then at higher orders, for example, at this one loop order, you also have so-called loop diagrams. So this means that there's a loop momentum to be integrated over, and therefore we not only get algebraic expressions, but also certain special functions such as logarithms, dilogarithms, and so on. And so that's called the next to leading order, and so on and so forth. Connecting again to the experiment, there's a yearly meeting at Les Houches in the Alps, where a certain wish list is compiled. And here you see an example of the latest one. I think this is from just a couple of years back, which kind of tells you about the state of the art. And details are not so important here, but it's essentially the case that for most processes, the state of the art is already at next to leading order. There's some wishes for calculation of next to leading order processes, in some cases even higher order. And this is really also where the bottleneck is in these state-of-the-art calculations. So as I said, in principle, if we want to go there, we could just draw all the diagrams and evaluate them, sum them up. But just to give you an idea that that's not so obvious, even at tree level, the number of diagrams actually, it grows factorially. So even from that viewpoint, it's not a trivial task to solve. And even more so at loop order. Now, this tree-level case already gives us a hint that there's actually more simplicity, that this straightforward approach is not the best one. And this actually has a lot of history. So there we can go back almost 40 years. In fact, so let me just reflect the state of the art from now, which is next to leading order with what it was in the 1980s. So there the state of the art was literally tree level. And people were saying, okay, there's a wish list. They knew 2 to 3 processes at tree level, and the equivalent of this wish list was to compute 2 to 4 processes. So this is, for example, well, some pages from a paper which printed the result for this process. Yeah, and you could have this idea, maybe that's just it. I mean, it doesn't have to have this question doesn't have to have a simple answer. But then there's a very beautiful story that, so Park and Taylor, they set out to compute what was on the wish list at the time. They evaluated the Feynman diagrams, did the calculations, and published the result like this. But they already had an idea that maybe that's not the end of the story, because they wrote this wonderful sentence. They said, so they had these 14 pages of results, and they said, we hope in the future, we hope to obtain a simple analytic form of the answer, making our result not only an experimentalist's, but also a theorist's delight. And in short, that's what they did. They came up with something, it's not the amplitude, but somehow the modulus of the amplitude squared, but it's a beautiful one-line expression. So details are not so important here, but it just shows you that some situations where there's a lengthy calculation, long result, 14 pages, and it really fits at the end of the day in one line. Now a lot of time has passed since the 80s, but in this amplitudes field, that's a recurring motive. And it's happened over and over again. And each time something like this was found, it also came along with some conceptual advance, some new understanding, some new methods that we are now benefiting from, and also the QCD colleagues are benefiting from. So this is just to give you an idea of this philosophy. And indeed, for people who compute amplitudes, there may be many different philosophies, many different motivations. So here I'd just like to show 2 of them, which I highlight here. So on the one hand, you could say, like this person here on the right, we have this motivation from experiments. So how can we manage, how can we compute those amplitudes that are relevant for the LHC? That's what we need. And then we want to make a plot and compare with the data. That's a very valid viewpoint. But then I just now described to you that there's also another viewpoint which says, how can it be that the result of those calculations are so simple? Shouldn't that teach us something? And maybe that means that there's also other ways for obtaining those results. Now, maybe you gather from how I'm presenting this that I'm a bit more on this side, but it's not. This is not to say that one viewpoint is better than the other. I mean, these are all coexisting good viewpoints. However, as I say in this talk, I'll adopt a little bit more of this viewpoint from the left. And in this regard, as I already mentioned, this idea of having mathematical data is very important. So we need formulas like these 14 pages from Park and Taylor so that we can study them and then figure out that there is some hidden simplicity in them. And so that's very crucial. By the way, if you have any questions, you can ask at the end, but also feel free to interrupt me, of course, at any time. So a few words about this amplitudes field. I've talked about the experimental motivation, and I've already hinted at that there's mathematical structures that are related to this. I think it's an important feature of this field that it has many different connections. So I mentioned these few, but there's also other connections to string theory, to integrability, and there's newer connections, applications to black hole physics, gravitational wave physics, and as I'll mention more in the talk, to certain aspects of theoretical cosmology. And to me, I think that's all those connections are a reason why the amplitudes field is actually thriving and profiting from this exchange of ideas. There's a useful cross-fertilization. And somehow to give you a more kind of numerical viewpoint of this, Jaroslav Trinka was so nice to give me this data, the numbers of participants from the amplitudes conferences. So there's a yearly conference in this field, which started roughly in 2009, and then has happened since, some COVID online version in between, but otherwise it's happened every year. And you can see there's a linear increase, let me call it in interest in the field. Okay. So that's what I wanted to say to introduce this area of scattering amplitudes. So now let me say a few words about this positive geometry, what that stands for. So this actually also goes back to 2009, this year of this first Modern Amplitudes Conference, and goes back to a paper by Andrew Hodges, who studied, again, tree-level amplitudes. So again, an old subject at the time, but he found something extremely interesting. So he found that for certain tree-level scattering amplitudes, they could be represented in a way that expresses them as volumes of certain geometric objects, of certain polytopes. So in particular, for some 6-particle tree-level amplitude, he found that this polytope here, which is defined via the kinematics of a scattering, is relevant. And so this also has a dual, this is a dual polytope. And it turns out that the amplitude up to some trivial prefactor can be written as the volume of this polytope P. And technically, this is the technical version of the formula. So that's a very interesting, completely new viewpoint. Has a lot of implications. Well, first of all, you don't see any Feynman diagrams in that formulation. It says it's the volume of some object. As such, it, however, encodes physical properties in a very different way. So this polytope knows about the singularities and discontinuities of the functions. In fact, they're encoded in the facet structure of this geometry. Now, I said there's no Feynman diagrams, so somehow the amplitude is computed as this whole object, but then you can think of, for example, triangulations of a polytope to obtain new representations of Feynman diagrams. So totally different from this original formulation. And another point I'd like to mention are positivity properties. So volume intuitively has you have the idea that it's positive, and indeed it shows that in a certain kinematic region the amplitude is positive. Moreover, and I'll mention that a bit later in the talk, you can also make a very strong statements about derivatives of the scattering amplitudes. Yes. Yes. So yes. So I guess there's two questions. So can we say something about strong coupling, and does this tell us something that we didn't know from Feynman diagrams? So for the second part, of course the answer for this, it was known in the 80s, right? These formulas were around. So of course you could have could have discovered many properties of the answer, but this one was only discovered in 2009, and I think, yes, this is precisely the point of this slide. I think this new representation, it makes manifest many properties that I would not have guessed from the Feynman diagram expansion. Of course, one could have guessed them, but it's not obvious in them. So this is not about whether one can, it's not about how does this change the state of the art and kind of computational or efficiency. It's really here making some conceptual points. So, for example, the Hodges paper is I think even in the title he talks about eliminating spurious divergences from amplitudes. So, just to explain what that is, the standard representation of a tree-level amplitude is expressed in terms of several terms, each of which has some undesired features that spurious poles. Now, this new geometric formula as a volume, it does not have these spurious singularities. So that's an example of a conceptual advantage. But again, I'm not saying that this is more efficient in any way. I'm saying it is a new conceptual viewpoint. Does that answer your question? Yeah, just to very briefly comment on the second part. So strong coupling, very important, very difficult question. There are some ideas relating to that. I'd be happy to chat with you later about this, where I think this the new formulation in terms of geometry has the potential that we can say some things to all loop orders. I can give you some examples later. Still, it's not easy because that's an intrinsically hard problem, but I think it also opens up some avenues. Okay, so yeah, thanks for the question. So these are indeed some of these conceptual benefits, I would say, from this new representation. The dots indicate that there's more, but for lack of time, let me continue. Now, Hodges' work was for tree-level scattering amplitude, actually a certain helicity sector, but for N particles. So these are just pure Young-Mills gluon amplitudes, but it's tree-level. So you could ask, well, does any of this generalize? What about loop-level amplitudes? And so there's good and bad news. The bad news is, at the moment, we do not know yet how to generalize this to QCD loop-level amplitudes. We also do not know how to generalize it to the non-planar sector. However, the good news is that there exists a loop-level version of this, which applies to a supersymmetric toy model of Young-Mills theory, N equals 4 super Young-Mills, and to the planar sector of that theory. So that is what I would like to mention next. So actually 4 years later, Nima and Yaroslav, they found a generalization of Hodges' formula, which now applies, first of all, staying at tree level, it actually applies to all helicity amplitudes. So all of the pure Young-Mills tree-level amplitudes, they can be represented as a volume of some abstract geometric object. But not only that, as I said, it applies to also all loop orders of this planar N equals 4 super Young-Mills theory. At the technical level, if we go back to these polytopes, a key feature in the definition is that the defining region, you can write it down as linear inequalities. The essential difference in the amplitudohedron is that I like to call it curvy. So there's some algebraic boundaries that define the amplitudohedron. And that's what makes it more difficult to handle. Okay, so we have this amplitudohedron. Now, I just like to, so I said this also applies to the loop order. I just now like to give you a kind of a toy example of how to think about this. In what way does it encode the loop corrections? Or more precisely, actually, the loop integrand. So here's a kind of the toy sketch of what you need to define a positive geometry. So we're in some ambient space of dimension D, and we're given some polynomial inequalities. So for some polynomial functions f in the variables in this space. And so these are the inequalities, and they can look linear, as in Hodges' case, or they can be curvy, as in the amplitudohedron. And then we define some, through the inequalities, some inside region here. So that then we call but that is okay, we have this region. And then it turns out that if your definition is a good one, if it's self-consistent and satisfies certain criteria, then this region comes with a canonical form which has only logarithmic singularities at the boundaries. So that means that so there's a form living on the space, and let's say there's some variable x where x equals 0 approaches some boundary, then this form will have just a simple pole near the boundary, and then there's a recursive definition. Then on the boundary you have the same type of definition again, just with dimension d one less. So again, this canonical form, if the conditions are met, then this is also a unique form that you can associate to this geometry. Here's a toy example. Let's just take the line segment as here. Then this is just the one form which has poles at the boundary of a segment, and it has a certain numerator which has to do with a normalization convention. And so here that you could just, so again, you see if you go to the boundary, you have a simple pole, and actually the numerator has chosen that the residue is just plus minus 1. So how is this? So this is a kind of a toy example. How is this connected to loop level super Young-Mills amplitude? So this canonical form, actually, it becomes the loop integrand of those amplitudes. So it saves you writing down all the Feynman diagrams and putting them together and simplifying them. It's just a first principle definition of what that loop integrand should be. So therefore, then we have a kind of a novel perspective or a way we could think about deriving loop corrections in such a theory where we have the positive geometry. We start by these inequalities. Mathematicians like to call it a semi-algebraic set. So it depends on some auxiliary variables, which will be the loop variables. And then also it can have some physical parameters x, which are the momenta or masses of the process. Here for a moment, I'm talking about massless amplitudes. And then in a second step, so you determine this canonical form, and that, as I said, corresponds to the Feynman integrand. And then once we have a form, we can think about what happens when we perform the integration. So when we integrate over a suitable integration region, we get the special functions that appear in the final answer. And so now from this perspective, there's also these related problems. So I told you that so far we have positive geometries for certain toy theories. N equals 4 super Young-Mills is one of them. But we'd like to find positive geometry for QCD, of a non-planar sector, and possibly other theories that are relevant. And so there's a question, what other positive geometries should we consider? Are there positive geometries that describe directly those physically important systems? Second point is perhaps a more technical one, but also a very important one. Once we have this beautiful geometry, how do we actually extract in practice the integrand from the definition? So this is for a mathematician, you might prove that the integrand exists and it's unique, but what's a constructive method of getting it? I'll also mention some ideas for that. And then finally, can we leverage this new insight about where the integrand comes from, this idea of a volume, to say something about the integrated answer? For example, are there some positivity properties that are now become obvious thanks to this new way of thinking? Sasha, I think you have a question. Yeah, great question. So can we generalize to other dimensions? Yeah, so ABJM theory, you just mentioned it, that is in 3 dimensions, so that's an example that exists. I don't think there's anything that ties it specifically to dimension. You also saw that there's this recursive structure, there's a recursive definition also connected to combinatorics. So it could be in principle any dimension. Of course, on the other hand, the physical theories that we most care about, they're in 4 dimensions. So yes, one thing I will say, you mentioned also regularization. I think that this is just my feeling, that having integer dimension is really, seems important to have many of these interpretations, these properties that I mentioned. So you could, of course, still, as a technical means, regulate something that you obtain from this, but so that would correspond technically to some twisted integrals, twisted period integrals. It's maybe not my favorite cup of tea, but I think you could do it. Yeah. Thanks for the question. So so you might ask, okay, so what do we know right now? Also related to Sasha's question. So actually, there was earlier this year at the KITP, there was a conference about particle theory, and also involved, as you can see from this cartoon here, some positive geometry. So there Jaroslav Trinka gave a talk, and he had this slide where he mentioned some of the positive geometries that we know as of now. So I have here this amplituhedron. Very interestingly, there's the isosahedron. So what is that? So you might think that somehow maybe supersymmetry is important to make that work. However, the isosahedron describes just matrix-valued cubic theories. So no supersymmetry whatsoever. So there it's really the combinatorics of the Feynman diagrams that links up with the positive geometry. And there's a variant of this called the cosmohedron, which is relevant in cosmological correlators. I'll mention that later. So this is actually already an active field of research, and I should say also before our grant. I mean, and importantly, there's a lot of mathematicians involved in this. So just as an illustration, I mentioned that there was 2024, there was a conference at Harvard about amplituhedra, cluster algebra, and positive geometry. And here you have a probably incomplete list of people who are already working at this intersection of math and physics. Yes. I think toric geometry, I could not tell you exactly how it's related, but it's certainly in the neighborhood of ideas. So I don't know, personally, I don't know much about it, but I have heard it coming up in discussions here. I'd actually love to learn, maybe we can chat a bit more about how toric geometry relates to this. Yes. Can we chat about this a bit more? I'd love to chat with you. Thank you. Yeah. So exploring this math connection. So when we got the news about the grant, we wanted to start out. In particular, my colleague Bernd Sturmfels at Leipzig. So here you see a picture from a workshop we had in February 2024, and this is just to give you an impression of also how many young people are between math and physics are involved in this community. So this was kind of a getting to know workshop between the mathematicians and the physicists. And fast forwarding by 1 year, there's already a very nice outcome of this, namely a special volume of a mathematics journal, Le Mathematische, many articles, and including some overview article, what is positive geometry. So especially if you're a mathematician or if you'd like to have a quick viewpoint, I recommend this to you. And hopefully in some words, as my friends, mathematics friends like to say, some context-free words that also may then be more accessible to mathematicians. So, so that's what I wanted to say to give you some idea of this math subject. Yeah, so really, I think it's important to have this also this different viewpoint of mathematics, because ultimately we want to find new positive geometries that describe QCD and other theories describing the real world. we might be lucky and find them just following our nose and playing with this and that object. But I think it's also very valuable to have a completely different math viewpoint. What questions would mathematicians ask? What definitions would they find natural? And so on. So I think that gives us a larger perspective. So then finally, let me introduce a third player in our grant, which are cosmological correlators. So let's begin again with some data, experimental data. So in cosmology, we're in a lucky situation that we have observations, for example, about the distribution of galaxies in the sky, and also data from the cosmic microwave background. And through the standard model of cosmology, this can be traced back to earlier times where it's expected that these structures that we see today, that they originated from some correlations at these earlier times. And then there's different models. This is not settled yet for what exactly is the physics at these earlier times that describes these cosmological correlators. And so therefore it's interesting to study these also again in various cases. So this is a little bit like this picture I had about the collider physics process, where there we were kind of going from the inside out, and here instead we're going from these earlier times where we're connecting this to the observations today. And here in our project we are concerned with these correlations in the early universe. So So it turns out that actually studying those correlations, very similar structures to those that I just talked about in amplitudes show up. Of course, it's a different context. We have field theory in curved space. There's different types of models. Again, we have some toy models. We have more realistic and complicated models. But so the general idea is similar. And I think the philosophy can be useful that this amplitudes field, as you have seen from these few examples that I've given you, people have been thinking about methods for computing Feynman integrals, scattering amplitudes for, let's say, 40 years or even more. And this particular field of theoretical cosmology, I think it's fair to say, is a little bit younger, and therefore can also profit from some of the things that have been understood in the amplitudes field. And so that's, I think, one particular reason to talk and see which of these amplitudes methods can be fruitful in cosmology. So just to give you some examples of what's already known. So in this paper from 2017, Nima, Paulo Benincasa, and Alex Postnikov, they found certain cosmological polytopes that describe individual Feynman diagrams in a cosmological toy model, particularly for conformally coupled scalars in the FLRW spacetime. So here's an example. So looking at this diagram here, let me not go through the details of what this stands for physically, but this is some example of a cosmological correlator, which has this expression here. So this you could derive probably in not so many steps through interpreting the rules for that diagram. But what they found is that equivalently this can be obtained from this particular polytope that's shown here on the right. So again, just like in the Hodges story, there's a positive geometry interpretation of this. Now this is, however, for this individual diagram, it is not as in Hodges for the sum of diagrams. Remember, Hodges' formula was just for all tree-level amplitudes. However, this is something that very recently there was some progress. So which involved Nima again, PhD student in Princeton, Carolina Figueredo, and PhD student in Munich, Francisco Vazao. They discovered a generalization of these cosmological polytopes. As you can see in this cartoon here, it's a bit more complicated. There's a more intricate combinatorial structure of the facets here, where the idea is that this cosmological polytope, it knows about all the different Feynman integrals that contribute to a cosmological correlator. And it's done in a certain way. It has the correct combinatorics to reproduce the correct answer. So here the advance is that it goes from an individual Feynman diagram to the sum of the Feynman diagrams. So this was very recent, just December last year. So, this completes my cast of characters, so scattering amplitudes, positive geometry, cosmological correlators. Now, having done that, I wanted to just give you some examples of more recent research that have come up in the context of the grant and in those areas. Now, of course, this is kind of a very personal selection. There's much more. I mean, you've seen this picture earlier of the many young people, so I possibly couldn't do justice to all the results that have appeared in the last year, but it's just a selection of some highlights that I'd like to share. So this is actually from a talk at this conference in February 2024 by Melissa Sherman Bennett, the mathematician who's now at UC Davis. And she talked about the tree-level amplituhedron. So here we're going back to Hodges, and I told you this is this generalization by Nima and friends to all tree-level amplitudes. So this object had existed since 2013, but in their work now, I think it's fair to say that they reached a complete understanding of the object, in the sense that they not only the object exists, but one understands its structure, and therefore one can answer questions such as, given the object, how could we write down the canonical forms? How can one tile the amplituhedron, and therefore then be able to write down a concrete formula from it? And moreover, they found that the tiles have interesting mathematical properties. In particular, they're connected to cluster algebras. Now, going to loop level, I told you, even though one has the loop amplituhedron, the definition is valid in principle to any loop order, there's a practical question: how do we actually write down the loop integrand? How do we write down that canonical form? We know it exists, it's unique, but how to get it? So in general, it's an open problem. And here's a new idea, which my student Elia worked on. So this is based on some earlier paper, and Elia and his collaborators, they generalized this to the two-loop order. Let me just describe the idea. So we have a positive geometry. The region here is this green region, just as a cartoon. Here it's the linear case, but as I said, in the amplituhedron, it's a bit, you should imagine it's a curvy object. Now, it was known that for polytopes, you have exactly this picture where, so you have the lines that bound the positive geometry. And so those, the facets here of the region P, those correspond to physical singularities. However, when some lines meet outside the positive region, those points correspond to unphysical singularities. And actually, this is something that one can use to constrain the integrand. The idea is that now if you can write down the canonical form as a product of the defining equations of those lines, of the boundaries, and then from that viewpoint, what you look for is the numerator function. So the numerator is some polynomial in your integration variables. And it turns out that then this numerator, it's uniquely fixed by demanding that it vanishes on those spurious singularities. So in other words, it's a way of bootstrapping the answer by imposing physically sensible criteria. In mathematics, this numerator function is called the adjoint curve. And so what Elia and his collaborators found that for analyzing the two-loop amplitude-hedron, that the same idea, which is guaranteed to work in the linear case, also fixed the numerator in this curvy case of the amplitude-hedron. So now we've come from tree level to loop level, but this is still the integrand. Now I'd like to tell you something new about the integrated functions. So this is work with Prashant Raman, who's a postdoc in Munich. And this is about a fascinating math property, which is called complete monotonicity, and which is related to positive geometry. So first of all, what is this complete monotonicity? So this is a property of a function, so the integrated scattering amplitude. And it says, first of all, that that function should be positive. It's very intuitive because we think of the amplitude as volumes. But then it says a lot more. It says also that the derivative is negative, second derivative is positive, and so on and so forth. So in short, it says that all these signed derivatives are positive, or non-negative if you prefer. So this is some concept which was introduced in the 1940s by Widder. And it also comes with some very nice characterization. So there's a theorem that whenever you have such a function, it has to have a certain Laplace representation like so. So this is just a Laplace integral, where the crucial point is that it has to have a non-negative kernel mu. So that's just a theorem. How do such functions look like? So we said they're positive. They have to be falling functions because the derivative is negative. Plots also look convex because the second derivative is positive. But then there's many more constraints. So here's just some particular functions where we investigated that property, and you can see that they have these plots at different loop orders. Now, I don't have time to go more into details of all of this. There's a lot more to be said. But let me just mention now that there's relations. So actually, I'll mention the Feynman integral connection in a second. But we also have good reasons to believe that this is tightly connected to positive geometry, particularly to this picture by Hodges. If you want to know more, please ask me after the talk. And there may be other relations to dispersive formulas, S-matrix theory, and so on. So here, just before finishing, I'd like to just mention some more concrete connection to Feynman integrals. So very much down to earth and possibly even useful. So it's actually easy to see that this, if you know about it, this complete monotonicity is very easy to see in scattering, in Feynman integrals. Here's a toy example. Let's take the massive bubble diagram in 2 dimensions. This has this particular Feynman parameterization. This is the diagram. These are the Feynman parameters. There's actually a GL1 invariant, so practically you can fix one of them to 1, and the other one is integrated from 0 to infinity. It's a simple integral. If you integrate it, this is actually the answer. And where x has some, is basically the momentum squared here. Now, if we take that answer and we plot it in the region where it's a real valued function, this is the graph you get. So it's exactly like what I advertised. Well, is it a coincidence? No, actually it's very easy to see if you look at that integrand, forget about the integration for now, the fact that it's a linear function x with positive monomials here just makes it obvious, just think about differentiating that the conditions, the defining conditions are met. So in other words, it's very easy to see just from the integral representation that this complete monotonicity holds. More generally, it actually holds for all scalar Feynman integrals within what we call the Euclidean region. So the Euclidean region is the region where this Feynman polynomial is non-negative. So that's some kinematic region. In this case, it's for x bigger than -4. So one can always ask this question: for given Feynman integral, what is that region? And then in that region, it's guaranteed that you have this complete monotonicity. So that's actually just what I'm saying here. Yeah, so this is a very general formula for Feynman parameterization, and as I just said, Euclidean region we define as the kinematic region where this f polynomial is non-negative. And then, as in the toy example, since this f is linear in the kinematics, you can easily convince yourself that complete monotonicity holds. Our math friends have a first paper where they study this Euclidean region under the name of copositive geometry of Feynman integrals. Now, what could this be good for? Let me just end on some work in progress with a student, Sarah Ditch and Prashant, postdoc I mentioned earlier. So in this project, we had the idea of combining this monotonicity property with differential equations. Differential equations are the state-of-the-art tool for computing Feynman integrals. But sometimes it's a bit tricky to solve them analytically or to obtain good boundary values. So here we thought, can we use let's imagine we have a situation where the differential equations that Feynman integral satisfies are known, and we want to benefit from this complete monotonicity inside. So that's what we did here. So we say, let's imagine that we have we can always choose a set of integrals which have complete monotonicity. So we have the differential equations, and now we want to benefit from the CM property. How do we benefit from it? Well, we take the differential equation, but now we impose that the solution should have a CM property, the function itself, and also its first n derivatives. And if we want to, we can go to any order n, because it's a property of all derivatives. Here's what you get. So this is essentially the plot for the bubble integral that I showed you before. The solid curve is just the function value that we knew because we computed it. This is just for checking. And here on the horizontal axis, we have the kinematics starting from -4 principal to plus infinity, which was our Euclidean region. Now we see that how strong the constraints are depends on the region we're looking at. So in this plot, white is the allowed region from complete monotonicity, and gray is the excluded region. So for example, here between -4 and -2, you see that the constraints are not very impressive. We just actually have this blue lower bound, and therefore this whole big white region is allowed. So not so useful. However, between -2 and 0, we actually have a lower bound and an upper bound. So here that's more useful. I've plotted these bounds for n equals 5. And what you can see here is that in this region, actually, it's optically not so easy to distinguish. So these are actually very close to the function value. And already they give many digits for n equals 5. And you can arbitrarily improve this by going to a higher number of derivatives. So that's just algebra. So in other words, in this region, the bound are very constraining, and we can just compute the value of the integral. And then finally, also very interesting, for x positive, we only have this lower bound again, but now something very curious happens, and we don't know why that happens. And I don't know if there's some linear programming optimization people in the audience, but what we see is that we only have a lower bound, but we observe that the bound and the function value, they're very close together. And if we increase n, we observe that it's really a convergence. We don't have an explanation for this. So to be conservative, we can say that in this particular kinematic region, we can honestly compute the function and we have convergence. But we also have this very interesting observation of really fast convergence, but in this case without proof. We don't know why the function wants to really lie exactly on the boundary. There's also then higher dimensional versions of this, of course, where you have some higher dimensional shapes, and the function value really lies exactly in the corner. Okay, I think it's time to wrap up. Before doing so, let me just quickly make 2 advertisements. If you're interested in any of this, we have a bi-weekly seminar series online, weekdays 4 p.m. CET. Anyone's welcome to join. The link is on our website, so drop us a mail. You're very welcome. Also, maybe this is a bit more for people who love these special functions in Feynman integrals. Together with Anastasia, who's there in the back, and Mark Spradlin, we're organizing a Symbology at 15 conference. So this is about all these wonderful mathematics that appears in Feynman integrals and associated. And you see, it's also a very happy topic. Okay, and finally, maybe not finally, next to finally, next spring, save the date, there'll be a 2-week, around Easter time, there'll be a 2-week PhD school in a lovely place in the French Alps. Here's a list of the confirmed lecturers as well. So this includes, again, both math and physics. Now, finally, like just to stop with the last advertisement, just on the 1st of July, we started a new initiative. It's called a Max Planck Center, which involves Max Planck Society, Institute for Advanced Study, and National Taiwan University. And maybe just in a nutshell, this is a project which is centered around these themes that are described, but it's not limited to them. So it's a larger initiative, and it's also open people-wise. You see some of the same protagonists here. But we're very open to having people who want to join, who feel like if you're working on anything and that's related, you feel this is interesting. So we have options of hosting people on visits, even sabbaticals. We'll have a series of events as well. And as I said, we're just starting. This is initially for 5 years. There's actually a first opening event in the first week of September at Taipei. So stay tuned if you for more information if you're interested. Thank you very much.
Okay, questions?
Thanks. I have a question about your last slide about positivity.
This one?
Yeah. Could you comment, say, in this region between, say, 0 and -1, where the bounds converge, is the idea that when you send n to infinity, there is a unique solution?
Absolutely, yes. We can pinpoint so roughly speaking, as you increase n, you get one more digit. You can really of course, it converges much better here compared to there, but also here, I didn't plot it for lack of time, but you would see this curve go down, and it really would snugly determine the graph. Mm-hmm.
And then you would say, because you know that this function is analytic, then you know it in a finite region, so you solve it, right?
So conceptually, definitely, but of course, if you know the function anywhere and you know the equation, you could then get it. But here we're also quite happy that we can just literally get the value. We don't need to use any Newton's method or any other method for solving the differential equation.
Other questions? Yeah, maybe one more quick question.
Just a naive question. I thought that the scattering amplitude as a quantum amplitude is usually a complex number, but are you saying that's actually real and positive?
Yeah, great question. So you're saying, okay, normally amplitudes are complex valued. We like to take modulo squared of them. A very good point. So this Euclidean region that I mentioned, that assures actually that we're in a regime where the amplitudes of the Feynman integrals are real valued. Now, you're right, it's an important practical problem that in most then physical situations, we want to analytically continue to, say, the scattering region where we have complex valued functions. So for example, from this perspective, that would be this region from -4 to -infinity, and one would have to take this value and analytically continue it over there, where you do have also then a complex, an imaginary part. That's absolutely right. So that's one of the open problems here. How to say? I mean, it's understood in general how to do this, but how can we do it efficiently given this information?
Okay, thank you.
It's time, so let's thank the speaker again.